Artificial amateurs aren't at all amazing. Analytically, ISO and amazing. Broken barriers bounded by the bombing. Buildings are broken, basically, and bombarding. Casually creating catastrophes, casualties, canceling. Cats got their canopies collapsing. Detonated diamond tank, daily do and do. Demonstrations, dawn dot on the down low.
Wow. Wow, that was fast.
I can do faster. I need some air.
A fast burst of stuff. And if this goes out on the radio, you could call that a fast radio burst. Huh?
I love it and I hate it at the same time.
I'm going to go with you love it.
It's heckin' fast. It's heckin' fast. That's the first verse of Alphabet Aerobics by the band, or by the group Blackalicious, I should say.
Okay.
Yeah. And that was the fastest rap I could think of that was radio appropriate, that I could do off the top of my head.
That was off the top of your head?
Yeah.
Wow.
Yeah. I got sick rhymes. But then once it gets to the second and third verses, my memory of these sick rhymes is less good.
I'm still impressed. Anyway,
yes, it's
welcome back, everyone, to season 5.
Wow, 5 seasons.
Time goes by fast when you're having fun, huh? Yeah.
Sorry. There's a bit of a delay in the sound effect I tried to use there. But yes, absolutely. Time has been going fast, and it is only getting faster. Our experience of time in this crazy, crazy world.
And that's what we're talking about today, everybody. The fastest things out there in, universe.
All right. So how are we going to do this? What kind of fast things are we going to be covering today?
We've got a whole bunch of fast things we could talk about. Let's get this episode over with fast. Well, I got a whole bunch of notes of some of the fastest things in the universe. There are some naturally occurring fast things. I have some man-made fast things. And then some proposed spacecraft type things, theoretical concepts that scientists and physicists have thought, technically this could possibly get a spacecraft up to X% the speed of light.
The speed of light.
And so, let's start with that one.
Okay.
That's the fastest thing in the Maybe we should have said that for the end, like built our way up to the fastest thing in the universe. All right, everyone, pretend you didn't hear that. Okay. Snails. Snails are
snails.
Now, speed of light. Boom.
Now we have to build up. So we start with snails, and then we go to slugs. Snails. Now, slugs are obviously faster than snails because they don't have to carry their house with them.
Don't have to carry the house. And
I know.
Slightly faster than that is the solar wind. Slightly faster. Well, compared to the speed of light, it is actually slightly faster than a snail. The solar wind is a stream of charged particles emitted by the sun that travels through space at speeds ranging from anywhere from 400 to 800 kilometers per second. And for those of you who don't live where Kovi lives, 250 to 500 miles per second.
Most of the world uses kilometers. I just have to say that. It's not Australians aren't the weird ones.
I learned my lesson as the guy who runs science actually on Facebook. And I always make sure to include metric units and imperial units. and I'm trying to be very, very good about that. So everybody
Okay.
gets the same experience. And
Okay.
last week, I put the imperial unit first and then the metric unit. I didn't think anything of it. I've been doing them both for years. And the flack I got. Metric, you should come first. I'm like, dude, it's not like you didn't see it.
Yes, the
Oh,
internet, where people will
internet.
read exactly what they want to read and not the context
Exactly.
or anything else.
Anyway,
Okay, cool. Yes, fast things.
fast things. So we covered the solar wind, and it's just the particles that are blown off by the sun traveling quite fast.
Yep.
Then we have other things that are also very fast. We have I have hypervelocity stars.
Mm-hmm.
They are
Hypervelocity
stars that
stars.
have
Yeah.
been ejected from galaxies or star clusters at ridiculous speeds, often after gravitational interactions with black holes. And
Mm-hmm.
one example I have is star S5 HVS1, everyone's favorite. And it's been measured traveling at speeds of 1,755 kilometers per second, which
That's
is
fast.
that's pretty fast. Which is anyone do the math fast in your head? Anyone? 3.9 million miles per hour. I don't know why I converted it from seconds to hours, but whatever. You people can reverse engineer that. It's fast enough to escape the gravitational pull of the Milky Way.
Wow.
That's pretty zoom.
It's quite zoom zoom,
Mm-hmm.
and it's quite wild to me when we think about often planetary scientists will talk about rogue planets. So these are
Mm-hmm.
planets that don't orbit around a particular star, and that's wild enough. But to consider that you have a star that has formed in some galaxy, and despite that, it has been yeeted out of said galaxy due to a gravitational interaction with a black hole. That's just mind bending to think about.
Yeet.
Yeet, screw. But yeah, it's incredibly impressive when you consider the fact that like galaxies are on the order of like tens of thousands of light years from side to side.
Mm-hmm.
So even moving at those speeds, it's taking like you have to get an incredible speed and then over time eventually get flung out of the galaxy. Crazy stuff. Hyper velocity, cool stars.
How soon until the Milky Way and Andromeda galaxies smush together?
It depends who you ask. Because
I'm
if
asking
you
Kovi.
ask, it's me. Yeah, if you ask some astronomers or if you ask cosmologists, technically the halos of the Milky Way galaxy and the Andromeda galaxy are already touching,
Mm-hmm.
right? So galaxies are made up of stuff that we can see, gases and dust and stars, and that's called the baryonic matter. And the baryonic matter, when you look at a galaxy and you see, oh, this like cool, pretty spiral thing, where that ends, the galaxies actually continue significantly beyond that as this dark matter halo of dark matter, which is interacting gravitationally with the galaxy. So, yeah, the dark matter halos are already touching, and it will still be a while longer. I can't, off the top of my head, remember exactly how many tens of millions of years, but we won't notice it when it
I was just
happens.
thinking that if you have a hypervelocity star that's traveling fast enough to break away from the gravitational pull of the Milky Way, but that's the Milky Way is, like you said, a very large place. It's going to take a long time to actually leave the Milky Way. And I was wondering if in
Yeah.
that time the Andromeda galaxy adds its mass to the Milky Way galaxy, that would increase the gravitational pull and then kind of maybe yeet the star back. Or no, yoink,
Yeah.
yoink.
the Lord yeeteth and the Lord yoinketh away. This is the rules of the universe. But yeah, we got a few billion years until that happens. So that star can keep on keeping on until then. Yeah. All right. What else? What other fast stuff you got for me today?
I
You
got
fast
black
talking
hole
man,
jet,
you.
supermassive black holes in active galaxies, otherwise known as some kind of a Q word. Eject
OEGN or quasar?
quasars. Eject
Quasar.
jets of plasma at nearly the speed of light. And these jets are powered by the black hole's gravitational forces, and they can reach very close to the speed of light, 99.999% of the speed of light. And that's awesome.
But you know what's even more awesome?
What?
Relativity.
I've heard of
Now,
that. Just a theory.
you've heard. Now, obviously, general relativity is super duper awesome. But in this particular case, it's actually the thing responsible for superluminal motion, meaning motion that appears to be moving faster than the speed of light. So when these jets are launched from a black hole, let's say, for example, depending on the alignment between our line of sight and the angle between our line of sight and the angle that the jet is being launched at, because of relativistic effect, it can look as if these jets are being launched faster than the speed of light. So
Okay.
the measured speeds will be faster than the speed of light.
Interesting.
I feel like I lost you. I had you and I lost you.
You had me, but it's like, okay. So,
Yeah. So
the jets themselves are not moving at the speed of light, but basically it's a matter of perspective.
Exactamundo. So
You look
in
at it from a certain angle in a certain way, it's like, oh,
yeah,
that's faster than Einstein said.
yeah. So just in our frame of reference, and given the angle that we're viewing the jet at, we can measure an apparent motion that's several times the speed of light, and that's called superluminal motion.
Awesome. Superluminal motion.
Yeah.
That's a fun
It's super duper luminal.
Super duper luminal. Speaking of supernova ejecta.
Yes.
Supernova ejecta. During a supernova explosion, material is ejected from the star at incredibly high speeds, and some of the fastest supernova ejecta measured can reach speeds up to 40,000 kilometers per second, or 25,000 miles per second, which is about 13% the speed of light.
Yes. So it's funny that you mention supernova.
I love those things.
They are some of my favorite objects to study because it's just like such an extreme environment for stuff to happen. You have these incredibly high temperatures. You have this super bright burst of electromagnetic radiation that actually is like less than 1% of the total energy of the explosion goes into that. Most of the energy actually goes into the production of neutrinos, which I think we might talk about later in this episode. But yeah, as you said, the actual physical shock wave that's being produced by the supernovae can actually get to velocities that approach scarily close to the speed of light. So some of the supernovae that I was working on recently in a paper that I just published were getting up to nearly 100,000 kilometers per second. So I think the fastest one in my paper that I measured had a shockwave velocity of 60,000 kilometers per second.
That's a shockwave that leaves the supernova before the ejected material leaves, which goes at a slower speed.
So, so the material, well, it depends what you're calling the ejecta.
Okay.
Basically, the shock wave that's produced from the supernova propagates outwards and it interacts with the stuff around the star. So you can kind of adjust your definition there, but basically that
Okay.
shock wave that's being produced by the explosion can be moving at those same significant fractions of the speed of light, and therefore any of the stuff that it picks up, and it's in that trail of carnage. No, it's wild. But yeah, that was one that we measured like 20 days after the supernova exploded. But then it will slow down over time as it interacts with other material. But then there were other supernovae in this paper that even years, like many many years after the supernova had exploded, the shockwave was still moving at like 10,000 kilometers per second as it propagates outwards
Ridiculous.
into space.
Ridiculous.
Redonkadonk. Yeah.
Donk donk. What else do we have as far as speed goes? Uh well, I have pulsars, which are rotating neutron stars,
Yes.
and they emit beams of radiation, and some pulsars spin incredibly fast. And with rotational speeds reaching up to and beyond 700 rotations per second.
700 rotations per second.
Right.
Wow.
When you think about the Earth, it goes around, makes one spin a day. So imagine doing that once a second or 700 times faster than that. It's
Yeah.
it's cray cray, as they say, the kids.
It's kind of on the order of there was this great video that a friend of mine, who's also a radio astronomer, Rami Mandow, or Cosmic Rami on all the social medias, made recently, videoing the inside of his blender, and the rotation rate of the blade in the blender is comparable to that of a pulsar. And so
Really?
when you look, there was a particular example that he was showing that was comparable. But basically, when you consider it, and you're like, oh, these blades are spinning around, X number of hundreds or thousands of times per second. You're like, okay, it's a small hunk of metal, no big deal. And then, by comparison, you take a neutron star, right, which is, on the order of a solar mass of material.
Right.
That's what's that? That's like 10 to the 28 kilos off the top of my head.
Precisely.
Or 10 to the 30, something like that, right? And that all of that stuff is all rotating at the same speed as the blades in a blender. It's bananas.
That's insanity. Ugh. It's fast. What started it off? Just boom.
Well, I mean, it's conservation of angular momentum, right?
It's true.
So you have the
All
thing
the
that's like
that's really tightly.
you have the big thing, and big thing is
Yes.
going like this, and then it collapses after the explosion, and then it goes, and then it starts rotating much faster.
But it's collapsing incredibly densely, so it's really
Yes.
cramping up that spin.
Much more dense.
You know better than I because this is your job. But how long will it take a pulsar to slow down? You can't do it forever, obviously.
Yes. No, that is a great question that I don't know the answer to off the top of my head. The spin down rate of pulsars. I want to say it takes millions of years, but I can't remember off the top of my head what the spin down rate is. So generally, when you look at the distribution of pulsars in the Milky Way, you see the faster rotating ones with stronger magnetic fields closer to the galactic plane, and as you move away from the center of the galaxy, you see the older ones that are spinning a bit more slowly. So, yeah.
Interesting.
Yeah, and I found that post from Rami, again, Cosmic Rami, on the socials. So his blender rotates at 170 hertz, so 170 times per second, and the pulsar that he's studying rotates at 218 hertz. Yeah. Wild.
All right. Neutrinos.
Yes. Neutrinos. Pew pew.
Pew, 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 is the sound of subatomic particles traveling very close to the speed of light. And they
Yes.
can pass through most matter undetected, making them incredibly difficult to study. But they go very, 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 very fast. Where do they come from? Neutrinos.
Well, I'm glad you asked, because as we were just talking about, the majority of the energy in supernovae from the explosion actually go into the production of neutrinos.
What is a neutrino?
What is a neutrino?
It's like
Well, how much time do we have?
a random neutron just zooming through the universe, or is it something smaller, different?
Yeah, it's not a neutron. So it's basically like it's an elementary particle, a fermion.
Okay.
Gosh. Basically, when you look at the standard model of particle physics, there are different types. There are two main different types of particles, right?
Right. I don't know.
We have.
Right. Oh, smart. I disagree with you.
That's fine. So you have bosons and you have fermions, right? So you have the bosons kind of you can think of as like making up stuff.
Sure.
Whereas, the fermions make up stuff, and the bosons are force carrying. So they're the things that carry the forces that govern the universe, right? So like a photon is a boson because it's the thing that's carrying the electromagnetic radiation force. And well, we can go deeper into it, but basically, neutrons are made up of quarks, electrons. Electrons on the other hand, and neutrinos are kind of their own form of fermions, kind of doing their own thing. We should do a standalone episode on the standard model because I feel like I'm not doing it justice.
Do it.
But yeah, neutrinos come in a few different flavors, and as you said, they are these super duper fast moving particles that move at almost the speed of light. They can pass through nearly anything. So, for example, if the core of the sun were to collapse, or any process that's producing light and neutrinos in the core of the sun, the photons that are produced, as those photons try to move out from the core of the sun to the surface, it will take millions of years, and then the 8 light minutes to reach us here on Earth. A neutrino, on the other hand, will pass through all of those inner layers of the sun instantaneously. Not instantaneously, but unbothered, because it won't. Most neutrinos will not interact with the actual material; they'll just pass right through. Yeah.
I think that's an episode all in itself, a neutrino episode.
Neutrinos, definitely. I mean, we'll definitely have to talk about like neutrino astronomers being the only astronomers that work underground.
I've seen photos and many articles I've written. It's ridiculous. These huge empty tanks underground with a little bit of water at the bottom. And
the Kamiokande neutrino detectors in Japan. They also have them at the Grand Sason mountain range in Italy, or Ice Cube in Antarctica, which is literally a giant cube of ice that, whole episode on its own. You're 100% right.
Oh, that's great. Okay.
Yes.
Wow. All right.
What else? What else? What else? What else moves fast?
What else moves fast?
It's a fast episode.
Fast episode. Gamma ray bursts.
Gamma ray bursts. How fast do they move?
I don't know. I didn't write down the speed. Nor did I realize I didn't write down the speed of fast radio bursts. Oh, gosh. I took my notes very fast as well. So that was bad of
fine.
me. That's fine.
So,
okay.
So gamma ray bursts and fast radio bursts are both bursts of electromagnetic radiation, and so therefore they would be moving at the speed of light, with the asterisks of the material that they travel through generally impacts how fast they move slightly. So it'll be just less than. But the reason why they're called fast radio bursts is not because they're moving fast, it's because the duration of the burst is very fast. The same thing goes for short gamma ray bursts as opposed to long gamma ray bursts. So they're just very, very short duration of the amount of time that the emission is happening for.
Oh, interesting.
Yeah.
Okay.
Yeah. And on the...
Go on.
Oh, sorry. I was just going to say on that topic of like how much stuff the fast radio bursts are passing through. This is why fast radio bursts, even though we kind of have an idea of where they might originate in terms of magnetars, these like really highly magnetized neutron stars, but we're not definitively sure. Why it's still interesting to study them is that the burst will get, it's called dispersed. Basically, it means that different frequencies arrive at slightly later times, depending on the stuff that it's traveling through. So the lower frequencies, a radio burst is coming across, let's say it's between 1 and 2 gigahertz. So the 2 gigahertz burst will arrive slightly before the 1.5 gigahertz part of that same burst, which will arrive slightly before the 1 gigahertz part of that burst, because basically the lower frequency has slightly less energy and it's more affected by the stuff, the kind of free electrons in the universe that it's passing through. And so by measuring that delay between different frequencies, what's called a dispersion measure, we can actually figure out how much stuff is in between us and the galaxy that fast radio burst is coming from.
That's awesome.
It's such a mind bender, right?
It is. It's on the order of awesomeness of spectroscopy. It's just they're looking at the wavelengths of something and the light of something. You can tell what it's made of, which is still freaky-ish cool. You can tell now this is something else where different wavelengths are coming at different times, ever so slightly, fractions of a fraction of seconds different, and you can just. It's ridiculous.
And we honestly should do a whole episode on fast radio bursts, because like when they were first discovered, they thought it was a glitch and it wasn't a real signal, and then they realized it was real and they found something that looked similar and they thought that was real, but it wasn't. It was actually just a microwave oven. It's a whole other story, but fast radio bursts are a huge part of the forefront of radio astronomy, my field. In fact, someone in the Australian community just this week was awarded the Australian Prime Minister's Prize in Science for his work on fast radio bursts. That's Professor Matthew Bales. Shout out if you are listening.
Thanks, man.
So, yeah.
We discovered stuff. Wow. Okay.
Yes. Fast stuff.
Fast stuff. Okay. Let's jump to some man-made fast stuff.
Mm-hmm.
I have made a top 10 list. I used to make top 10 lists for science actually all the time. Top 10 tallest, top 10 fastest, top 10 heaviest, all these types of things.
Okay.
And some of the fastest spacecraft ever created are still out there right now, zooming along. Uh, most famously, everyone thinks Voyager 1 launched in 1977. That's got to be the fastest because it left the solar system and all that stuff, but it is not the fastest. It is traveling at a pitiful 61,000 kilometers per hour. That's nothing.
Per hour? Nah.
That's bupkis. It's nothing. It's idiot. Uh, but some of the top 10 fastest spacecraft ever created by us. Number 10 was Ulysses,
Mm-hmm.
launched in 1990 at 40,600 kilometers per hour.
It's pretty
Then
good.
Pioneer 11, launched in 1973 at 41,000 kilometers per hour. New Horizons,
Mm-hmm.
launched in 2006, made it all the way to Pluto, which is still a planet, and 58,000 miles per hour.
Dwarf
Then you
planet.
have Voyager 1, which is what 61,000 like I mentioned. Pioneer 10 is out there still traveling, launched in 1972 at
Mm-hmm.
131,000 kilometers per hour.
But the fastest, wait,
What?
the
What?
fastest the fastest human-made object,
Yes, is. Come on.
the Parker Solar Probe.
It is indeed the fastest,
Yes.
but not always the fastest.
Sometimes it likes to have a lazy Saturday afternoon.
Absolutely, it does. Its job is to orbit the sun and get really close to the sun and then loop
Right.
away from the sun and then get back to it.
Yes.
While it's
Yep.
coming close to the sun, it sets so far the ultimate speed record of man made objects of 691,870 kilometers per hour. It is
Whoa.
insanely fast when it goes in for a nice dip into the sun's atmosphere, I guess you could say. The corona.
Benjamin, can I quiz you on the physics of that? Can I ask why is it that if you have this probe that's orbiting around the sun,
Yeah.
why why does its velocity increase when it goes down closer to the sun?
It's falling towards the sun, isn't it? The closer you get to the sun, the stronger its gravitational pull, and it pulls you faster. Yes, no, close.
Yes.
It's got rocket boosters and lasers.
Pew, pew. The answer I was looking for, in the same way that I made that connection before with the neutron star rotation to conservation of angular momentum, here we're talking about conservation of energy, in this case from potential to kinetic energy, right? So, so when you are higher up in the gravitational potential well, higher up above this, gravitational source, you have more potential energy. And then as you move down, you're losing potential energy, but gaining kinetic energy, which corresponds to velocity,
Right.
right?
Yes.
And so as it gets down to the closest part of its approach, it will have its highest speed. Basically, if you have anything orbiting anything else in space, right? And it's
Right.
doing, like, let's say it's not a perfectly circular orbit, but it's an elliptical orbit where it has a closest approach and then it yeets itself out further away. Its maximum speed will always be at its closest approach and its minimum speed at its furthest distance.
Kepler's second law.
Conservation.
Am I right? Yes, I'm
Yeah,
right.
sorry to everybody listening with headphones who just heard my pew pew pewing so loudly.
Let's go back and listen to me get that Kepler thing right again. Yeah. The
Uh,
fastest crewed spacecraft.
like poorly designed.
No, it was a spacecraft. It was Apollo
Oh,
10.
crude as opposed to
Crude, not
crude.
crude as in CRUDE, but crude as in CREWED.
I see.
The fastest spacecraft with people on board was
Yes.
Apollo 10. On its return to Earth from the moon, it reached just a hair under 40,000 kilometers per hour. It is the fastest
Whoa.
spacecraft with people on board to have yet traveled. They just hit the right mark on the way back from the moon, and they ran their
Bananas.
thruster just a little bit longer than anybody else did because these things were everything was calculated, but it was still just a bunch of guys on board pushing the button to make it go. And so they ran it a little longer, just by fractions of a second longer, and they hit that one corridor just the right way. Things just happened to line up, and these three men are the fastest traveling people in the history.
Wow.
And
That's
one of my
yeah.
yes, it's
No, go on.
crazy.
That's crazy.
One of my favorite little uh footnotes in all the reading I did for fastest man-made objects
Hmm.
was a manhole cover.
Oh yes, we've discussed this guy
We've
before, haven't
discussed this
we?
before. I think we did it on the Space Case show. But it was my favorite little thing. It's called the Operation Plumb Bob manhole cover. Um, Back in 1957, doing all the nuclear weapons testing that we did, one nuclear weapons test was called Operation Plumb Bob, and it was in New Mexico. And what happened was a hole was dug 500 feet straight down, and a nuclear bomb was put down at the base of it. And then they sealed it off the top of this hole with a 900 kilogram or 1 ton manhole cover made of steel and concrete. And that they thought will keep the blast down so they can see what happens when they detonate a nuclear weapon underground. And what happened was the 2,000-pound manhole cover did not stay put, and instead it was launched directly straight up at a speed of 241,000 kilometers per hour. And
Allegedly.
well, there's a photo. There's a photo from when the explosion literally is about to begin, or just starting to make the ground rise, and the manhole cover is there. And then there's another, and they took a series of photos because they did the best they could to take as many fast photos as they could. A fraction of a second later, there's this big burst of like smoke and some flame a little bit coming out of the ground. The ground is breaking. And at the very top of the photo, there's this dark thing with like soot shooting off the back of it, going straight up. It was the manhole cover. So they have a starting point, and a fraction of a second later, another, and they know the altitude at that little thing so they can gauge the speed. And the part of it that I love the most about this thing, it is uh, way more powerful than the escape velocity needed. So it could have left the atmosphere, but it was also traveling so insanely fast that it most likely evaporated from the friction of the air around it and from the heat of the blast itself. But if
I
it
love
did
it.
keep intact, it would have been to space in 1.5 seconds if it
I
kept
think
going.
I think we've discussed this in the context of the history of space flight, because
Yeah.
if it didn't disintegrate, upon interacting at that speed with particles of gas in the atmosphere, then not only would it have been the first human-made object launched into space, but it would also have been the first object to escape the gravitational pull of Earth and the solar system at the speeds that it was moving at. It would be, basically like a rogue manhole cover,
Yes, just zooming
essentially.
through the
Just
universe.
yeah, just gone. Oh man, I love it. I love it. Oh, you know what? There are two things that we forgot this
What's up?
episode. Well, we did not do an ad.
We did not do an ad. Oops. We're just going.
We didn't do an ad, and we didn't cover the only thing that is potentially as fast, if not faster, than the speed of light. And I happen to have something that covers both of those things.
Bring it.
Are you tired of waiting for your messages to arrive?
Yes.
Are you fed up with those pesky data caps? Well, we're introducing GraviWave, the messenger service that's out of this world. Our cutting-edge technology harnesses the power of gravitational waves to deliver your messages at the speed of light. No more delays, no more buffering, just pure, unadulterated cosmic communication. So the next time you want to send a message that's light years ahead of the competition, choose GraviWave, because who needs Wi-Fi when you've got the universe?
That's great. I think that's one of my favorite ones. I think that's probably going to be my favorite one. I think that's my favorite one.
No.
I think that's my favorite one. GraviWave.
GraviWave.
Yeah, I like it.
It's good. It's good. We approve.
Who needs Wi-Fi? I got universe.
because the speed of light. I mean, the speed of light is the fastest things can travel within the fabric of space-time of our universe. But gravitational waves are ripples of the space-time itself. They're not a thing traveling in space-time. They are the movement, the fluctuations of space-time itself. Yeah.
How all the spaceships in Starfleet are able to talk to each other.
Allegedly.
They probably use GraviWave. They probably use GraviWave.
Yeah. Either GraviWave or they're just launching manhole covers at one another.
Oh my god. Oh my god. Like this is a weird cosmic skeet shooting.
Yes, it was a delayed ad, but it did manage to include what I think is the most fascinating and wild and fast-moving thing that we know of. Gravitational waves.
I like it. I like it very, very much. GraviWave. Oh. Okay.
All right. This has been good. I feel like we have covered things that were faster than people expected, whether it's gravitational waves or the apparent superluminal motion of jets from supermassive black holes or jets from neutron stars merging, another thing that can produce these jets. But yeah. So yeah, go home right now and Google superluminal motion. It's wild.
I'm sure it is.
Also, the images that people have produced of like this kind of, when you have this explosion of a neutron star, that basically it explodes and there's a cocoon that the jet is escaping out of. And there's some like really brilliant work that's been done by Ehud Nakar and other people on like actually modeling how these cocoons and jets work, and they seem to do a pretty good job of matching the things that we're observing. And the things that we're observing seem to show these kind of wild superluminal motion. Again, it's an effect. It's not actually moving faster than the speed of light. It's just an apparent motion. But yes, sorry to go back to that. This has been good. I definitely enjoy how off track we got this episode.
Not really. We stayed pretty on track. For all our friends and fans who are listening, please write us and let us know how off track or on track we were. We want to hear from you about anything. So tell us how awesome we are, or not.
Yes. Where can people find you if they want to tell you how awesome you are or are not?
If people would like to tell me I'm awesome or not awesome, you can do so by trying to track down Science Actually on Facebook, Threads, uh, Twitter, Instagram, Mastodon, Hive, LinkedIn, and also by carrier pigeon. How about you, Kavi?
Unfortunately, we're not accepting carrier pigeons at this time. However, you
Oh, you gotta
are.
get on that. You gotta get on that.
I'm sticking to tin cans connected by pieces of string, because that way I can have each tin can labeled and I know exactly who the call's coming from before I pick it up.
Smart.
Can't hide your caller ID with a tin can. So you can find me at Fun Fact Science on all of the good and bad social media. And you can find us on, if you want to find us on Spotify or Podcast Addict or any of your favorite podcasting apps. But you can also find us on TikTok or YouTube if you want to see our faces. And see the various shenanigans and weird expressions that we make during these recordings.
It's worth it. You'll love it. Well, like Tommy just earlier described the conservation of whatever something, and he had his arms out, and then he brought his arms back in, and he spun around in his little spinny chair. And you guys in just audio land, you didn't hear any of that, but people in video land, you get to see the whole thing.
The whole conservation of whatever it was. Yes, you can see that whole thing. I love it. All right. And feel free to let us know if there are any topics that you would like us to cover in future episodes, or if there are any guests that you would like us to reach out to interview. We love a good guest. And we have some good ones coming up. We have some astrophysicists who work on gravitational waves and pulsars and active galactic nuclei. You'll be hearing
also have
from them.
an astrophysicist working on a project going on the Europa Clipper to Yep, I've been talking with her a lot. So when she gets back, she's ours.
Yes, very excited for that. So stay tuned, subscribe, like, follow, do all the things, and you will be able to hear that and much, much more on future episodes of The Nerd and the Scientist, presented by Science Actually.
Thanks, everybody.